welcome to another session of Thermodynamics tutorial. I am Thananka Sutia and I'm a PhD student at IIC Bangalore. So we'll wait one more minute and then I will share my screen and we'll start our class today. Yeah, hello. So welcome you all. In today's class, we will be doing mainly the sums that are related to the combustion processes, like when a fuel combustion takes place, what is the air fuel ratio, and what is the molar fraction, what is the air fuel ratio by means of mass, what is the air fuel ratio by means of molality. These all things we will be dealing with, and the prerequisite for this is the previous two classes, basically the properties of mixtures of gases and the properties of the steam. Okay. So let us go to the first question. 2 kilomole of octane is burned with air that contains 40 kilomole of air. Assuming the products contain only carbon dioxide, water, oxygen, and nitrogen, determine the mole number of each gas in the products and the air fuel ratio for this combustion process. Okay. So, in order to do this, the first step will be to write down the combustion equation. Okay, so combustion equation will be okay, so the combustion equation will be 2 moles of C8 okay, and it reacts with 40 kilomoles of air. Okay, so the 40 kilomoles of air, this is, now I'm writing this as O2 plus 3.76 N2. Can anyone guess where from this 3.76 N2 came? This is because the air contains 79% nitrogen and 21% oxygen. This is by volume. Okay, so if you divide these two, that means for each and we also know that volume fraction is corresponds to the mole fraction, okay, of any particular compound I. The volume fraction is, it corresponds to the mole fraction. Okay, so that means if there is one mole present, so if there is if there are 21 moles of oxygen, then there are 79 moles of nitrogen. So that means if there is 1 mole of oxygen, this will be basically 79 divided by 21, that is equals to 3.76. okay, so this came from here. Okay, so this is the reactant side. So why, because it is telling that 2 kilomoles of octane, it is burnt with air that contains 40 kilomole of air. Okay, now it tells us that the products only contain carbon dioxide, water, oxygen, and nitrogen. Okay, so we don't know how many number of carbon dioxide moles are there, so we assume this as x number of moles of carbon dioxide. Okay, plus y number of moles of water vapor or water, whatever is possible. Okay, and then let us say z number of oxygen are present. Okay, and w number of nitrogen comes out. Okay, So you have to tell the number of mole number of each gas in the products. That means you basically you have to determine x, y, z and w. Okay, and after that you have to determine the air fuel ratio for this combustion process. Okay. So in order to determine this number of moles, that means this x, y and z for this chemical reaction, what we have to do, we have to simply go by conservation of mass. Okay, so conservation of mass tells us that that the mass of the reactant will be equal to the mass of the product. Okay, so that means whatever number of moles of carbon is present on the left hand side, that should be equal to the number of moles of carbon present in the right hand side. Whatever number of hydrogen atoms are present in the left hand side should be equal to the number of hydrogen atoms that is present on the right hand side. Whatever number of oxygen atoms are present in the left hand side should be equal to the number of oxygen atoms on the right hand side. Okay, so that means number of atoms of each element in the reactant side must be equal to that in the product side. In the product side. Okay, fine. So now we will do mass balance for carbon first. What we will get, so from here it is 2 into 8. Okay, so no any carbon is there, and here carbon is basically is equals to x. Okay, so that means x is equal to 16. Next I will do balance for hydrogen. Okay, so hydrogen, it will be 2 into 18, that will be equal to hydrogen here, yeah, 2y. So that means my y is equals to 18. Okay, now let us do the balance for oxygen. Okay, oxygen will be 40 into 2, that is equal to 2x. Okay, plus y. Okay, plus 2z. Now we already know x and y, so this will be 80. 2 into x is nothing but 32. Okay, and y is 18 plus 2z. So from here z will be equal to 15. Okay. So we have got x, y, z, and now the next is for w. So now we will do balance for nitrogen. Here the nitrogen present is only 40 into 3.76 into 2. Okay, and this will be equal to w into 2. So this is 150.40. Okay, so we have got, therefore the complete combustion reaction is two C8H18 plus 40 plus 3.76 N2. Okay, and this side it will be 16 CO2 plus 18 H2O plus 15 O2 plus 150.40 N2. Okay, so therefore number of moles of product is equal to what? Carbon dioxide 16, water or water vapor, whatever is there, it is 18, oxygen it is 15, and nitrogen it is 150.40. Okay. Now next part is you have to determine the air fuel ratio for this combustion process. Now they are not telling us about anything like air fuel ratio based on the mass or air fuel ratio based on the molality. So we will basically do air fuel ratio based on mass. Okay, it is nothing but the ratio of the mass of air divided by mass of fuel. Okay. So what is the mass of the air? This is the air part, so you have to just calculate the mass of this air. So how many moles of oxygen are present? 40 into 2. Okay, so 40 moles of oxygen are present, and 1 mole of oxygen is 32, so it will be 40 into 32. Okay, then 40 into 3.76 moles of nitrogens are present, and 1 nitrogen is of 28, so this will be 40 into 3.76 into 28. This is the mass of the air. Now what is the mass of the fuel? This is the fuel. Okay, so the mass will be 2 times of C8H18. Okay, so what you will get? 2 into 8 into 12. This is for the carbon part, and 2 into 18 into 1. This is for the hydrogen part. Okay, so this is kg of air, and this is kg of fuel. Is clear, everyone? So the air fuel ratio is 24.08 kg of air by kg of fuel. Okay. Okay, so let us go to the next question. Determine the air fuel ratio on a molar basis and on a mass basis. Now it is mentioned that both on the molar basis and on the mass basis you have to calculate for the complete combustion of octane for theoretical air and 150% theoretical air, that is 50% excess air. Okay. So let us first calculate for theoretical air. So what is the initial step? That we have to write down the combustion equation. So we already know ethane formula is C8H18. Okay. Now we don't know how many. In the previous question it was given to us that 40 kilomoles of air was used. Now we don't know how many kilomoles of air. Let us assume this as A. Okay. Fine. Then uh, since this is the theoretical air, so the complete combustion without any excess air is there, so no oxygen will be produced, so only the products will be carbon dioxide, water vapor and nitrogen. Okay, and let me assume that these are B, C and D. Okay, now from conservation of mass, C 8 is equals to B, so this implies B is equals to 8. Then hydrogen 18 is equals to 2C, so this implies C is equals to 9. Okay, then oxygen, it is 2A is equals to 2B plus C. Okay, so from here 2A 2B is 16 plus 9, so A is basically 25 divided by 2, and that is 12.5. Okay, now then we will do this same for nitrogen, that is A into 3.76 is nothing but D. Okay, so from here D is equals to 12.5 into 3.76. This is 47. Okay. So therefore the complete combustion reaction is C8H18 plus, you've got A is equals to 12.5, so this will be 12.5 times O2 plus 3.76 N2. Okay, and this will give you 8 CO2 plus 9 H2O plus 47 N2. Okay, So therefore air fuel ratio on a molar basis, this will be basically number of moles of air divided by number of moles of fuel. Okay. Air fuel ratio on molar basis. So number of moles of air is what? 12.5 into 1 plus 3.76, isn't it? So this will be 12.5. Number of moles of oxygen 1, number of moles of nitrogen 3.76. Okay, this is the number of moles of the incoming air, and number of moles of the fuel is 1. Yes or no? Fine. So this will be kilomole of air by kilomole of fuel. Okay. So this is 59.5 kilomole of air by kilomole of fuel. Okay. Similarly, air fuel ratio on mass basis. Okay, so this will be 12.5. Okay, so 12.5 into this is what? 32. Plus 3.76 into 28 divided by, so ethane it is 8 into 12, 18 into 1. Okay, kg of air by kg of fuel. Okay. So this is 15.05 kg of air by kg of fuel. Okay, so this was when you have used theoretical air. Now in the second case, it is being told to us that you are using 150% theoretical air. That means there is 50% excess air. Okay, 150% theoretical air or 50% excess air. So what it will happen, that in the reactant side we did not have any oxygen here. Now in the reactant side there will be some number of moles of oxygen will also be present. Okay, so C8H18. Okay, now you are using 150% theoretical air, that means 50% of the exercise, so this will be 1.5 into whatever the theoretical amount was required. The theoretical amount required was 12.5. Is it clear here? Okay, this will be O2 plus 3.76 N2. Okay, now this will be 8 CO2 9 H2O plus some X amount of O2 will also be present, and how many nitrogen will be present? This one into this one into this one, because nitrogen goes unreacted, isn't it? So this will be 1.5 into 12.5 into 3.76 N2. Okay, now from here we will do conservation of mass for oxygen in order to get the X value. Okay, so for the oxygen this is 2 into 1.5 into 12.5. this is the left hand side part of the oxygen. This will be equal to 2 into 8. Okay, and this will be plus 9 plus 2x. Okay, so from here 37.5 minus 16 minus 9 divided by 2 is equals to x. So from here your x is equals to 6.2. Okay. So you might be worried about like how I have already written this 8 9 and without writing. You can put it in some variable. This won't have any change. The only change will be because it is already taking combustion and whatever amount, so total amount, that is like a saturation, so total amount of air that whatever you give, if you give excess amount, so these products will not be changing. The only changing will be that more amount of oxygen will be left in the reaction. Okay, so whatever amount of oxygen is left in the reaction is used as this X. Okay, so now therefore the complete combustion reaction is C8H18 plus, if you multiply this 1.5 and 12.5, 18.75. Okay, then this is 8 CO2, then this is 9 H2O, then this is 6.25 O2, and then (74.5) N2. Okay, so therefore air fuel ratio on molar basis. Okay, so this will be 18.75 into 1 plus 3.76 divided by 1. Okay, this is 89.25 kilomoles of air by kilomole of fuel. Okay, similarly, air fuel ratio by mass is what? 18.75 into 32 plus 18.75 into 3.76 into 28. Okay, divided by 8 into 12 plus 18 into 1. Okay, this will be kg of air divided by kg of fuel. Okay. 22.57 kg of air by kg of fuel. Okay. Okay, so the next question is calculate the minimum volume of air required to burn 1 kg of coal having the following composition by weight. Carbon 72.4%, hydrogen 5.3%, nitrogen 1.81%, oxygen 8.5%, moisture 7.2%, sulfur 0.9%, and ash 3.9%. You have to assume normal temperature and pressure condition, that is pressure is equal to 1 atmosphere and temperature is equals to 293 Kelvin. Okay, so first of all, we know that burning takes place, burning or combustion takes place in presence of oxygen. Okay, so let us check how many. So first step is to calculate the required oxygen amount for combustion. Okay. So what is the required amount of oxygen that is required for combustion? Now what are the products that you can undergo combustion? So carbon can, if it is fully combusted, it is undergoing carbon dioxide. So the first reaction of combustion is this one. Okay, now 12 kg and this is 32 kg. Okay, so 1 kg is what? 32 by 12. Now remember, these are all based on composition by mass. That means there, if we assume that the total mass of the what you call coil is, let the mass of the coil, let the mass of coil equal to 1 kg. Okay, then how many kg of carbon is present? 0.724 kg of carbon is present. Okay, so that will be equal to 32 by 12 into 0.724. okay, so this is equals to 1.93 kg. Okay, similarly, will it go undergo? Yes, so it can form moisture, H2 plus O2, this gives H2O. Now you can balance, you will not balance, doesn't matter, so this will be 2 and this will be 2, so 432. So therefore how many is present here? 0.053, isn't it? So 0.053 is nothing but 32 divided by 4 into 0.053. okay, zero 0.424 kg. okay, then next is nitrogen. It is something which does not undergo reaction with oxygen because nitrogen is mostly unreactive. Okay, moisture, it is already there, oxygen, it is already present, so what it will do now, one more thing is there, is that sulfur. Okay, so sulfur can undergo combustion to form sulfur dioxide. okay, 32 and this is also 32. So how many sulfur is present? 0.009 kg of sulfur is present. Okay, so 0.009, so that means it will be 32 by 32 into 0.009. okay, that is basically 0.009 kg. So therefore total oxygen required to burn 1 kg of coil is what? This one plus this one plus this one, that is 1.93 plus 0.424 plus 0.009. okay. So 2.363 kg. okay, so this much kg of oxygen is required. okay, now in this coil this much percentage by mass of oxygen is already present. okay, okay, so amount of oxygen already present is equal to how much? 8.5%. it means in 1 kg it will be 0.085 kg. so therefore amount of oxygen required is what? 2.363 minus 0.085 kg. okay, 2.278 kg. So this much amount of oxygen is now required. Now we know that since air contains 23% oxygen by weight. Remember the last when I was talking about in the first question, it was 21% oxygen by volume. Now this is 23% oxygen by weight by mass. This means what? That is 100 kg of air corresponds to 23 kg of oxygen. Now why we did this? Because you are required to calculate the minimum volume of air. Now first you have calculated the amount of oxygen that is required in kg. After that, if there is this much amount kg of oxygen, how many kg of air will be required? So 23 kg of O2 corresponds to 100 kg of air. Okay, therefore 2.278 kg of O2, it will be equal to what? 100 by 23 into 2.278 kg of air. Okay. So this is 9.9 kg of air. Fine. Now it is telling nothing, so this means this is an ideal gas. So and you are given the pressure, you are given the temperature. Okay, so from here you can calculate from ideal gas equation P is equals to rho R T. Okay, or what you can write as PV is equals to MRT. Now from here volume will be what? MRT by P. Okay, what is M? M is 9.9, and I think you till now you know the value of R, that is 0.287 kilojoule per kg Kelvin, whatever. Temperature given to you is 293 Kelvin because it is in normal temperature and pressure, and the pressure is 1 atmosphere, so it is 1.013 into 10 to the power 5 Pascal. So that will be basically 1.013 into 10 square kilopascal. Okay, so from here you will get the answer in volume. So this much minimum amount of air, volume of air is required for the combustion of this given blah 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 samples. Okay. So the answer is 8.218 meter cube. This is the minimum volume of air that is required for the combustion. Okay. Fine. Now let us go to the next question. Ethane is burned with 20% excess air during a combustion process. Assume complete combustion and a total pressure of 220 kilopascal. Determine the air fuel ratio and the due temperature of the product. Okay, the first part we have already done such type of questions. We will do this again, and then after this, using the given pressure value, how can we calculate the dew point temperature of the product? Okay, now just in place of your octane, ethane is given. Okay, so the first part will be for theoretical air you have to calculate, and then you have to calculate for the excess air. Okay, for theoretical air. Okay, so ethane formula is what? C2H6. And let me assume this one is A O2 plus 3.76 N2. Okay, and this will give you B CO2 plus C H2O plus D N2. Okay, so again mass balance for carbon, this will give me B is equals to 2. Mass balance for hydrogen, this will give me 6 is equals to 2C. So this implies C is equals to 3. Okay, and then mass balance for oxygen, this will give me 2A is equals to 2B plus C. Okay, this implies your A is nothing but 2 into B is 4 plus 3 by 2. 7 by 2 is nothing but 3.5. Okay, and then balance for nitrogen will give you A into 3.76 is equals to D. Okay, so this implies D is nothing but 3.5 into 3.76, that is 13.16. Okay, so therefore for theoretical air, the complete combustion reaction is C2H6 plus the A value is what? 3.5 O2 plus 3.76 N2. Okay, value of B is 2 CO2, the value of C is 3 H2O, and the value of D is 13.16 N2. Okay, now for 20% excess air, okay, so what it will happen? C2H6 plus 1.2 into 3.5. okay, and this will be O2 plus 3.76 N2. okay, this will give you 2 CO2 plus 3 H2O plus some X amount of oxygen will be there here, which will be remaining unreacted, and then how many will be there for nitrogen? 1.2 into 3.5 into 3.76. okay, so 1.2 into 3.5 into 3.76 N2. okay, so solving for oxygen, what you will get? 2 into 1.2 into 3.5 is basically equal to 2 into 2 plus 3 plus 2x. So this implies x is equals to what? 21.2 into 3.5 minus 7. Wait, wait. So x is equals to 0.7. Okay, so therefore the complete combustion reaction for 20% excess air, 20% excess air is what? C2H6 plus this is 1.2 into 3.5, 4.2 O2 plus 3.76 N2. Okay, and then this will be 2CO2 plus 3H2O. Okay, and plus 0.7O2 and plus this will be 0.5 176 15 point 15.79 15.79 N2. Okay. So now the air fuel ratio. Okay, therefore air fuel ratio is equals to what? 4.2 into 32 plus 4.2 into 3.76 into 28 divided by 2 into 12 plus 6 into 1. Okay, so this is kg of air divided by kg of fuel. Okay. 19.219 kg of air divided by kg of fuel. Okay, so this is the first part which we have already done in case of octane also. So the next part is to calculate the dew point temperature of the product. Okay. Now how to do this? Dew point temperature. Okay, so dew point temperature of the products is the temperature at which water vapor water vapor in the products starts condensing. Okay, so that means you have to calculate the saturation temperature for water vapor, and for that you have to know the partial pressure of water vapor. Okay, so how we know the partial pressure of water vapor? For in order to do that, we know now number of moles of water vapor, that is NV. How many number of moles of water vapor are present? 3. Okay, then total number of moles, this is basically N, and this will be number of moles, total number of moles in the product. So 2 plus 3 plus 0.7 plus 15.579. Okay, 2 plus 3 plus 0.7 plus 15.79. Okay, so this will be your plus 3 plus 0.7 plus 15.79. Okay, so this is 21.49 kilomole. Okay, so therefore Dalton's law, what it says, PV by P total is equals to NV by N total. And remember, P total is given to us as 220 kilopascal. Okay, so from here we can get the PV is nothing but NV 3 by 21.49 into 220 kilopascal. So this is 30.7 kilopascal. Okay, which is approximately equals to your 0.03 megapascal. Okay, so now you have to just look at T dew point. T dew point is nothing but T saturation at PV. So we will go to the steam table and we'll find out at 0.03 megapascal what is the T saturation. Okay, so this is the steam table. So see, at 0.032 it is there, and at 0.02 it is there, so we need at 0.03. Okay, so we will do a linear interpolation. Okay, by linear interpolation. Okay, so at whatever values it is there, at 0.032 it is there, and at 0.0, okay, can I take this at much more finer value, 0.031 it will be basically. Okay, it will be basically 0.031. Okay, so 0.032 minus 0.028, 0.028 divided by 0.032 minus 0.031. This will be equal to 70.586, 70.586 minus 67.518, 70.586 minus T dew point. Okay, so from here T dew point will be nothing but 70.586 minus 0.767. So this is basically 70.586 minus 0.767, 69.819 degree Celsius. Okay. Fine, if you have any doubt you can ask. Okay, so the next question is, consider a fuel with equimolar mixture of propane and a natural gas, that is methane. Then determine the stoichiometric air fuel ratio on a molar basis, and the molar air fuel ratio for a combustion at an equivalence ratio of 0.8. Okay, so so what we will do in this case, we will do individually what is the air that is required for combustion of propane and also for natural gas. Okay, so let us first do for propane. C3, that means this is theoretical air required for theoretical air required for combustion of propane. Okay, so theoretical air required for combustion of propane, C3H8 plus A times O2 plus 3.76 N2. This will give BCO2 plus CH2O plus D N2. Okay, so for carbon you'll get B is equals to 3. Balance for hydrogen will give you 2C is equals to 8, so this implies C is equals to 4. Okay, and then balance for oxygen will give you 2A is equals to 2B plus C. This will give you A is equals to 2 into 3 6 plus 4 by 2, that is 5. Okay, and also for nitrogen you will get A into 3.76 is equals to D, which implies D is equals to 18.8. Okay, similarly theoretical air required for complete combustion of methane. Okay, again here also CH4 plus A prime times O2 plus 3.76 N2, this gives B prime CO2 plus C prime H2O plus D prime N2. Okay, once again solve for carbon, you'll get B prime is equals to 1. Solve for hydrogen, you'll get 4 is equals to 2C prime, which gives C prime is equals to 2. Then solve for oxygen, you will get 2A prime is equals to 2B prime plus C. Okay, so this implies A prime is equals to what? 2 into 1 2 plus 2 by 2, that is equals to 2. And similarly D prime, sorry, for nitrogen, that is A prime into 3.76 is equals to D prime, so this gives you D prime is nothing but 2 into 3.76 7.52. Okay, so therefore theoretical air complete combustion reactions are C3H8 plus, in the first case we got A as equals to 5. Okay, so this will be 5 of O2 plus 3.76 N2. Okay, so this will give you is 3 CO2 3 CO2 plus 4H2O plus 18.8 N2. And CH4, here you have got A prime is equals to 2, So it is 2 into O2 plus 3.76 times N2. Okay, 3.76 times N2, and this will give you CO2 plus 2H2O 2H2O plus, and this is your 7.52 N2. Okay, so therefore number of moles of oxygen required to burn 1 kilomole required to burn 1 kilomole of C3H8 is equals to 5. And similarly, number of moles of O2 that is required to burn 1 kilomole of CH4 is equals to 2. Now what happens, in the question it is telling us that it is an equimolar mixture of propane and methane. Okay, so if the number of moles of propane and the number of moles of methane are the same. Okay, so given that the fuel contains equimolar mixture of
साला तोर दुस्ते दुस्ते छोड़ दिलियो एकरा हटा
yeah, so it contains equivalent, so that means if, okay, let the number of moles of fuel is equals to 1 kilomole. Okay, therefore number of moles of C3H8 is equals to 0.5 kilomole, and number of moles of CH4 is also equal to 0.5 kilomole. Okay, therefore number of moles of oxygen required for complete combustion of the fuel is equals to what? For 1 mole of this propane, 5 moles of oxygen is required, and we are present here 0.5 kilomole. Okay, so that means it will be 0.5 into 5. Similarly, for 1 kilomole of methane you require 2 kilomoles of oxygen, so this is your 0.5 moles are present into 2. So this much kilomole number of oxygen will be required. Okay, so this will be basically 3.5 kilomole. Okay, fine. Now what happens, we already know that since air contains 21% oxygen by volume. Okay, therefore V of oxygen divided by V of air is what? 0.21. Okay, and we also know that the mole fraction of ith component is basically proportional to the volume fraction of that same component. Remember, we have already done this, that P V A is equals to N A R T, and P V T is equals to N T R T. Now if you divide this one, then you will get V A by V T is equals to N A by N T. So this is basically the mole fraction X, and this is basically the volume fraction of the 8 element, and this is the mole fraction of the 8 element. Okay, so the volume fraction and the mole fraction are basically the same. So therefore what we can write from here is that the number of moles of air in 3.5 kilomoles of oxygen is basically what? 3.5 divided by 0.21. Okay, 16.67 kilomole. Okay, therefore air fuel ratio is what? Number of moles of air, because we are told to find out the air fuel ratio based on a molar basis. Okay, so this will be number of moles of air by number of moles of fuel. Okay, so number of moles of air, we have got this as 16.67, and we have done the entire calculation based on taking the 1 kilomole of air. So this is basically 16.67 kilomole of air divided by kilomole of fuel. Okay, now the next part, it is telling us to find out the molar air fuel ratio for combustion at an equivalence ratio of 0.8. Now for that you have to know what is equivalence ratio. Okay, so equivalence ratio is nothing but ratio is the ratio of the air fuel ratio, the stoichiometric air fuel ratio divided by the actual air fuel ratio. Okay, now here remember we have done the calculation for this based on the complete combustion of air and assuming theoretical air, that means no excess amount of air, oxygen is present in here. So whatever we are getting, the air fuel ratio is basically the stoichiometric air fuel ratio. So this is basically my air fuel ratio stoichiometric. Okay, now equivalence ratio is given to us as 0.8. Okay, we already know this stoichiometric air fuel ratio is 16.67. So from here we can calculate the actual air fuel ratio. this will be 20.83 kilomole of air divided by kilomole of fuel. Okay. Let us go to the next question. A natural gas has the following molar analysis: CH4 80.62%, C2H6 5.41%, this is the 1.87%, this one 1.62%, and this one. Now the gas is burned with the dry air, giving products having a molar analysis on a dry basis. So this was the dry products that was obtained, and this whatever percentage is given based on the dry product. Okay, now you have to determine the air fuel ratio based on a molar basis. Okay, then you have to calculate the amount of product in kilomole that would be formed if this is the volume of the fuel mixture, and temperature and pressure is given, and you have to assume that the fuel is an ideal gas. Okay, and then you have to determine the percentage of the theoretical air that is required. Okay, so first of all, what we will do, we will assume that let us consider 1 kilomole of fuel. Okay, so amount of fuel that is present is 1 kilomole. So therefore the reaction will be, that is the combustion reaction will be in the form of, remember this percentage are given on a molar basis. So if 1 kilomole we are taking out, we are taking as the total mass, total number of moles is 1 kilomole, so this will be 0.8062 CH4 plus 0.0541 C2H6 plus 0.0187 C3H8 and 0.0160 C4H10. Okay, and then this will be 0.1050 N2. So this is the fuel part. Okay, now it is allowed to react with air. Okay, and we don't know what is the number of moles of air present, so let us assume this as A. It will be O2 times 3.76 N2. Okay, now reactant has got two parts. One part is the wet part and the other part is the dry part. Now if there are B moles, if there are 1 moles of dry product present, so then this will be, carbon dioxide produced will be 0.078 carbon dioxide. So that means if there are B moles of dry product, so that will be 0.078 into B. Okay, similarly this will be 0.002 carbon monoxide. Okay, then oxygen 0.07. Okay, and then nitrogen 0.85. Okay, these are the dry products. Plus we also know that whenever we burn any hydrocarbon with oxygen or air, it gives carbon dioxide plus water plus other byproducts, but here this water vapor is not there because this is in the wet part, so we'll assume this one as C into H2O. So what it means actually, this means that 1 kilomole of fuel, okay, there exist B kilomole of dry product and C kilomole of wet product. Okay, so this means what? Here we have assumed 1 kilomole, so for here the product formed are B kilomoles of dry product and C kilomoles of wet product. Okay. Now from conservation of mass, okay, so we'll balance for carbon now. So we'll do balance for carbon. What do you get? 0.08062, 0.8062 plus 0.0541, 0.0541 plus sorry, this is 0.0541 into 2 plus, then this will be 0.0187 into 3, 0.0187 into 3 plus 0.0160 into 4, 0.0160 into 4. Okay. And this will be equal to B into 2 into, sorry, B into 0.078 this will be equal to B into 0.078 plus one more carbon is there, 0.002, 0.002. Okay, so from here B is equals to 12.93. Okay, then we will do balance for hydrogen. Okay, hydrogen, 4 into 0.8062, okay, plus 6 into 0.0541 plus 8 into 0.0187 okay, plus 10 into 0.0160, okay, then this will be equal to 2 into C. So this implies C is equals to 1.93. Okay, then we'll balance for nitrogen. Okay, so uh, 0.1050, 0.1050 plus A into 3.76 is equals to B into 0.85. So this implies A is equals to 2.89. Okay. So you have got 2.89. Therefore, the balanced chemical reaction is 0.8062 CH4 plus 0.0541 C2H6 plus 0.0187 C3H8 plus 0.0160 C4H10 plus 0.1050 N2 plus 2.89 O2 plus 3.76 N2 gives 12.93 into 0.078 CO2 plus 0.002 carbon monoxide plus 0.07 O2 plus 0.85 N2 plus 1.93 H2O. Okay, therefore air fuel ratio on a molar basis is equals to what? 2.89 into 1 plus 3.76 divided by 1. Okay, 13.756 kilomole of air by kilomole of fuel. Okay, moving on to the next part of the question. In the second part, we have to calculate amount of products formed in kilomole. Okay, so given conditions of the gas, given P is equals to 1 bar, V is equals to 100 meter cube, and T is equals to 300 Kelvin. Okay, so what we know, PV equals to N R star T, where R star is the universal gas constant. So from here we can find the number of moles of the fuel. Okay, so P is 100 kilopascal, volume is 100, R star is 8.314, and your temperature is 300. So you'll get this one as 4 kilomole. So for 1 kilomole, number of moles of the product is equal to what? 12.93 plus 1.93. With products and byproducts, isn't it? 12.93 plus 1.93. Okay, 14.86 kilomole. Okay, therefore for 4 kilomoles, 1 kilomole of fuel. So for 4 kilomole of fuel, number of moles of the product is equals to 4 into 14.86 kilomole .44 kilomole. Okay, fine. Then let us go to the next part. Theoretical percentage of air. Percent of air. Okay, so number of moles of oxygen required in the reaction. How many moles of oxygen is required in the reaction? So you can see that 2.89 was added, and in the product it is already left here 12.93 into 0.007. So actually how many are required here? 2.89 minus 12.93 into 0.007. 0.07. Okay, so that is basically 1.98 kilomole. Okay, now since air contains 23% oxygen, by mass, by volume it contains 21%, isn't it? So since it contains 21% oxygen by volume, okay, so therefore number of moles of air in 1.98 kilomole O2 is basically 1.98 into 100 by 21 kilomole. Okay, number of moles of air present in 2.89 kilomole O2 is basically 2.89 into 100 by 21 kilomole. Therefore, percentage of theoretical air is equal to what? 2.89 into 100 by 21 divided by 1.98 into 100 by 21. So you'll get this one as 145.9 percentage. Okay. Okay, so let us go to the next question. A biofuel consisting of 90% oxygen and 10% ethanol is burnt with 25% excess of air. Calculate the following. You have to calculate air fuel ratio by mass, carbon dioxide ratio, mass, and product ratio of the mass. Okay, so for that let 1 kilomole of fuel is taken. Okay. Now theoretical air consumption. That will be 0.90. Octane is what? C8H18. Okay, plus 10% ethanol, that is 0.10 C2H5OH. Okay, and we don't know what is the theoretical air required, so this will be O2 plus 3.76 N2. Okay, and this will give you BCO2 plus CH2O and DN2. Now we have already done this, so if you do carbon balance, you'll basically get B is equals to 7.4. Now if you do hydrogen balance, you will get C is equals to 8.45. And if you do oxygen balance, you will get A is equals to 11.575. And if you do nitrogen balance, you will get D is equals to 43.522. Okay. This we have already done so many times, so I am skipping this step. Now therefore for 25% excess air, okay, 0.90 C8H18 plus 0.10 C2H5OH plus, since 25%, so this will be 1.25 times 11.575 O2 plus 3.76 N2. Okay, so this will be 7.4 CO2 plus 8.45 H2O plus, let me assume that this is some amount of oxygen is present, EO2 plus 1.25 into 11.575 into 3.76. Now from here, if you do again the balance of oxygen, okay, what you will get, basically E is equals to 2.893. okay, so therefore complete combustion reaction is 0.90 C8 H18 plus 0.10 C2 H5 OH plus 14.468 O2 plus 3.76 N2, okay, gives 7.4 carbon dioxide plus 8.45 water vapor plus 2.893 O2 and plus 54.40 N2. Now once you got the balanced reaction, it is very much easy for you to calculate the air fuel ratio on mass basis is basically what, 14.468 into 32 plus 14.468 into 3.76 into 28 divided by 0.90 into 12 into 8 plus 18 into 1, okay, plus 0.10 into 2 into 12 plus 6 into 1 plus 16. Okay, put all these values you will get 18.527 kg of air by kg of fuel. Okay, next is carbon dioxide ratio. Okay, so CO2 ratio is what, mass of the carbon dioxide that is present in the product side. So this will be basically 7.4 into 44 divided by this entire M fuel. Okay, and if you put this, you will get 3 kg CO2 per kg of fuel. Number C, product ratio is basically the 7.4 into 44, okay, plus 8.45 into 18 plus 2.893 into 32 plus 54.40 into 28 divided by m fuel, and if you do this you will get 19.348 kg product by kg fuel. Okay. So with this I conclude today's this was the last question which I was about to do. Now I will wait for 10 more minutes. If you have any doubt you can ask me. Okay. So we'll meet in the next class. Thank you for listening.